Good evening, everyone. Welcome to the third live interactive session on geosynthetics and reinforced soil structures. This week, till the previous week, we saw uh, the types of geosynthetics. Then we studied the main mechanism how the geosynthetics actually reinforce the soil. Then we studied the properties of geosynthetics, all those things, right? And also we then studied the uh, testing, the main test. Why do you need to test geosynthetics? Why is testing essential? And what are the various test of many types of geosynthetics? Mainly we focused on geotextile geogrids. So we learned about the various tests. And in this week, in week third lecture, actually we will be going through the going through going focusing mainly on reinforced soil structures. Right. So basically, we will be dealing only with the reinforced soil structures. We will be seeing the basics, and this is mainly a descriptive. As you have already gone through the lectures of this week, you saw that this there are no problems involved. Right. So mainly it was just a theoretical portion. That's the descriptive part of the course. There were hardly any numericals. There were no numerical or no problems involved. So what we will be doing is that we will be just revising the concepts little bit, and then we will be solving some problems from basic part. Right. The basic is retaining wall part because that should be clear, right? And in the next week we will be seeing how to design this reinforcement structure. So this week we will be just going to the basic theoretical part, the basic concepts, and in the next week we will be seeing how to actually how can we design this reinforcement structures. Okay. Okay, so before we start, I wish all of you a very happy Independence Day. So, as we all know, today is the 77th Independence Day we are celebrating. So, wishing all of you a very happy 77th Independence Day. Okay, so the first question, today's question that we need to answer is why do we need retaining walls? Okay, what is the need of retaining walls? Retaining walls, you see retaining walls all around you, right? Everything. Okay. Basically, you go to some building to park your car in the basement. You see retaining wall there. Then you travel in the roads, in the highways. You have flyovers. You see retaining walls there. Yeah. So we see retaining walls everywhere, right? So why? What is the need of retaining wall? Okay. Why do we need retaining wall? That is because we know, soil has high compressive strength, right? But soil is very strong in compression. It can take compressive loads, but it has limited tensile and shear strength, right? So it is very weak in tension, and it also fails in shear, right? So because of that, what we need to do sometimes a need arises that we support the soil by some means of some external means. So that external means is nothing but our retaining wall. So we need to support the soil so that it stands by its own. Right? So say you take sand in your hand, and what you just take sand in your hand and you just keep pouring sand from your hand. You just keep pouring. So what will happen? The soil will form a heap like that, right? Soil will form a heap like that on the ground. So this angle, which actually the soil forms, this angle is actually nothing but the angle of repose. So this angle, there is certain angle. That angle depends on the strength of the soil, right? And the strength of the soil means the friction of the angle of the soil. So higher the friction angle of the soil, the steeper the angle the soil can make. But what if we want to make the soil stand like this. Okay, so like this side, completely vertical 90 degrees. Then is it possible? So by naturally it isn't possible, right? So what we do, we construct a retaining wall so that the soil, we can support the soil and the soil can actually stand, right? So we have put some lateral support on the soil, and to that lateral support, what happens? The soil stands by its own. Now, obviously, if we are providing some support here and the soil, so the tendency of the soil is to flow, is to take it stable, this one, right? Stable configuration. That is, it tends to form like this, right? It tends to flow. So what will happen in that case? Just what will happen? The soil will actually put some pressure on, right? So that pressure, and that is nothing but the active earth pressure, right? So the soil will be putting some active earth pressure, and due to that pressure, there will be tendency for the for the retaining wall to displace from its position. So what we need to design the retaining wall such that this retaining wall can actually resist that particular active earth pressure, okay, and all the other external forces that are acting, okay. So why do we need retaining wall? So to support the soil laterally, okay, as soil is okay. Now next comes the types of retaining, right? So what is this first one? What is this? Which retaining wall is this one? Which type of retaining wall is this one? Can you identify which type of retaining wall is this one?
Gravity retaining.
Yes, gravity retaining, right? It is gravity retaining wall. So in gravity retaining wall, what happens is that maybe the weight of the structure, right? The weight of the wall, that is what that resists the active thrust or the other whatever forces that are coming. Okay, that is the weight of the wall, and generally it is made up of this plain concrete only. Okay, this is a huge structure. What we do is made up of generally made up of plain concrete. Okay, so that is the gravity retaining wall. And then what is the second retaining wall? Which one is that? Say second and third both. What are these?
It is RCC retaining.
What?
RCC retaining.
Yeah, RCC, that is cantilever retaining, right?
Yeah,
So
cantilever. Yeah, cantilever.
RCC cantilever retaining wall. Okay, RCC cantilever retaining wall. So here you can see the stem is actually much slender, much thinner, not that thick, right? So because it is RCC, we are using reinforcement so that it is strong in tension and bending, right? And here you can see that the at the top, what happens? The top, see, in a cantilever at the top, at the free end, this moment demand is less, right? Moment demand is lesser. So here we have this cross section is thinner, and as we go down it becomes, the stem becomes thicker. Okay, so this is known as the stem, and this is nothing but the base of the retaining wall, the foundation of the retaining wall. And below that, one more interesting thing you can see is that this shear key. Okay, so there is a shear key that is there at the base. This also, the shear key actually helps prevent the sliding of the retaining wall by, because we there is development of some passive pressure here. Okay, some passive resistance develops here. And due to this passive resistance, this shear key actually helps the retaining wall to have higher factor of safety in sliding. So it prevents the retaining wall to slide to the active. And this portion is known as the heel. This is the heel portion. This is the toe portion. Heel portion because it's like a feet, right? So it rotates about the toe and the heel. Actually, there is a tendency for the heel to go up. So it is known as the heel. Okay. Then we see some more retaining walls. So this is the counter fort retaining wall and this is the buttress retaining wall. So in both of them, you can see there are some counter forts or buttresses. So these two are almost similar. So in counter fort retaining wall, what is done is that these counter forts are actually given on the side of the backfill. And buttress means these buttresses are actually given on the other side. So this side we have the backfill and this side is buttresses. Okay. So these are the counterfort and the this buttressed walls. Okay, buttressed. And can you identify this structure here? What is the structure here shown here? The third image. What is that structure that is shown here? This structure is also kind of retaining structure, right? So here you can see that the soil level is almost up to here, and inside you can see an excavation has been made. So the soil, there is no soil inside. Right? Inside also see the excavation is in ongoing. Yeah, from here also soil is being excavated out. Now outside you can see the soil is there up to almost the top level, almost. Right? And inside there is some excavation that has been done. This structure, whatever you see here, this structure is widely used mainly in offshore construction, like for constructing these bridge piers, okay, river bridges, and those sea bridge piers and all. So these structures are used regularly there. So can you identify that? What is it? So that is actually sheet pile. Okay, so here you can see the sheet piles. These are the sheet piles. This all these are the sheet piles, and what you do, you have to drill that into the soil. Right? There are some tools available which you drive the sheet pile into the soil, and there is some interlocking between the sheets. So these two sheets like this, they will interlock here. Okay, there is some interlocking, and what you need to do is that you need to drive it. And after driving, what you do? You just excavate the soil from inside. So here, what you can do is, let's say outside there is water. Okay, so you drive the sheet pile. Then what you do? You excavate. You pump out the water from inside. Okay, you drive the sheet pile, you pump out the water from inside, and then what you can do, you get a dry environment inside the sheet pile, and there you can start your construction of the foundation. So whatever, if you're constructing as a fire, bridge fire or something, you can do that. You can do piling or whatever you want. Okay, pile cap and top that you can make a this bridge fire, whatever. So you get a dry environment inside. So this is very fast construction method, right? So just you need to drill the sheet pile, and so it will just form a wall. And one more thing is that if you see here, you can see this brace. So these are actually a braced sheet pile wall. Okay, so some bracings are actually given. So so that this sheet pile actually gets more strength. Okay, okay. So soil is pushing from outside. Okay, so to prevent it from collapsing, some bracing is also. So you will see one more type of sheet pile bracing in the next slide. Yeah. So this one you can see sheet piles you can see again here. So here you can see sheet piles. These are the sheet piles. They are in one line, they are arranged, and these are anchored at the back. Okay, these are one more type how we can install sheet piles. So to give more strength to the sheet pile so that it does not fall out, what is done is that some anchors are actually there is some there are some anchors that are given so that there is some special resistance due to which this sheet pile gets more strength. All right. Then in this second image is also for sheet pile. So you see these are the sheet piles that are placed this way, and these structures at the center, these are nothing but the braces. Okay, brace. So you can see these are the sheet piles here, and with the help of the struts, okay, the struts, what we are doing is that we are bracing the sheet pile. So what we can do is we can start this trailing. Okay, so what you can do, you can put, first of all you can put the sheet pile up to this height, say. Okay, then what you will do, you will brace it, then again you will dig up deeper, then you will again brace it. So like this you can go down, top down approach. If you want to follow, you can do that. All right. Okay, so these are basically anchored, these are anchored sheet pile, these are braced sheet piles. Okay, these are the braced and this is the anchored. Then you can see here some stages are shown. Okay, stage one is excavation, stage two is bentonite, this one mud, it is being sprayed. Stage three is the placement of reinforcement, and the stage four is the pouring of. Okay, this is similar to this pile construction, right? The construction of piles. So this is actually no, these are actually known as diaphragm walls. So what we do is that we construct spile-like structure is closed intervals. So due to which what happens, the kind of retaining structure is formed. Okay, kind of retaining structure is formed. Those are known as this diaphragm. Okay. Okay. Now the most important portion of part where we need to focus. Okay, where this force comes into play. This is the reinforced earth or reinforced soil retaining wall. So we cannot use the word reinforced earth because it's patented by someone else. So we need to use the term reinforced soil. So these are nothing but reinforced soil retaining, right? So the first image you see is of the general type of reinforced soil retaining walls that we use. So you can see here we have the concrete foundation or this base, this leveling pad that we can leveling pad. Now of the leveling pad, you see this modular blocks, right? So there are blocks that are placed. So in the class, in the lecture classes, this was already discussed, right? So modular blocks. So there are some modular blocks that are placed, and in between these modular blocks we have some reinforcement that is placed between the soil that is to be retained. Okay, so what we do, we reinforce this some part of the soil, and this is the nothing but the other this backfill soil. Okay, so with the help of geosynthetic material, what we do, we reinforce the soil, and these modular blocks are not rigid, right? This can move. So this allows some amount of deformation to take place, because of which the less strains actually develop in the wall, and there is low chances for this facing of the wall to collapse. Okay, so you can see here at 3.6 meter high, this wall is shown where you have this 0.3 meter wide modular blocks placed, and this with the help of this modular blocks, our reinforced soil is been constructed. Okay, so this part is the reinforced soil part, and this part is the other retained soil part. Okay, and all of this soil is called the backfill. Okay, and this is the reinforced part of the backfill soil, and another part is the other retained part of the backfill soil. Okay, so gravity retaining walls that we saw, those gravity retaining walls can be only constructed up to say 2 to 3 meters. Okay, but the reinforced soil walls can be constructed up to large height. to almost 100-meter height. Okay, so this RCC retaining this cantilever retaining walls maybe up to 10-meter height. Gravity retaining walls maybe up to 2 to 3 meter height. Okay, RCC cantilever retaining walls maybe up to 10-meter height. But this reinforced soil retaining wall can be constructed till huge heights, up to almost 100-meter heights. These are constructed. Okay, more than 100-meter high. These RCC retaining walls are constructed. Okay. Okay, so here you can see this nailed. Okay, the nailed portion, nailed walls that are shown here. Okay, so this walls, this there is nails. Okay, nails are steel reinforcement or reinforce these nails. Nails are used to actually reinforce the soil. Okay, this is the machine that is actually used to drill the nails. Okay, after see first what we do, first we drill the hole, then we insert the nails, and then we fill that hole with the cement grout. Okay, cement grout. So in that way we do the nailing process, and at the head of the this we put some reinforced steel plate. Okay, so due to this soil nailing, what happens, we will see that the soil slope can actually take up more weight. Okay, higher load it can take before failing, and also these are more stable. Okay, so here you can see without this nails, this soil would actually fail along this slide. So but what we are doing is that we are reinforcing the soil with the help of this soil nails. Okay, the soil nail actually helps in strengthening the soil and thus reinforcing the slope. What? Okay. And this face you see is covered some net-like structure, maybe geoglyphs. This is just for the facing, okay, so that this debris doesn't fall. Just a facing, some geosynthetic is laid down. Okay, so these were the initial this this type of this retaining wall, reinforced retaining wall that were actually constructed. Okay, initial reinforced retaining walls that were constructed. Here you can see some precast concrete blocks at the front, and then we use some tie anchors to tie that at the back of the soil. Okay, so these were the initial, and same similar to this we can see here. So here we are using the tie rods, right? And here in this case, place of these rods, what you're using is using some ladder-like reinforcing element. Okay, so these are the earlier initially what concept developed for this reinforced soil. So these are the initial concepts that developed. Okay, so let us just watch this video edit. Just a second. Just watch. So this is how actually this soil nailing is done. Okay, how this soil nails are actually put into the soil and constructed. What I will do. So this is the installation. See, first you need to mark the position of the soil nails, right? So first what you do, we mark the position of the soil nail, then these holes are drilled with the help of drilling rods. So drilling rods, what you can do, if you have seen SPT, these rods, right? Drilling rods are similar to these SPT rods, SPT test. If you have seen SPT test rods, so these drilling rods are similar to these SPT test rods. So these drilling rods are actually first used to drill the soil. Okay, first what we do, we use this machine to and the drilling rods. We can put extensions in front of these drilling rods, and what we do is that we drill the soil. Okay, so here you can see this drilling is, it's not visible clearly, but see, drilling is done, and what we do, you use air to flush out the soil from that hole. And see, this is the drilling that is going on. See, these are the pipes or the drilling rods that are used, similar to the SPT. Those are used for to drill. Okay. Then what we do after drilling, we put the reinforcement or the nails, soil nails inside the this. We put the soil nails inside these drilled holes. Okay, see this you see here. This is a this soil nail. Okay, this reinforcement, this thin rod-like thing. You see that is nothing but this. So what they are doing is that they will carry that. So they see they are carrying it, carrying the rod, and they will just put that inside that drill hole. Okay, so after we put, what we do is that we, as I had said, what we do is that we put some cement grout. Okay, we put some cement grout in that hole, that so that this nail is actually firmly placed in that soil. Okay, we put some cement grout. Okay, so in that borehole there is the reinforcement, and we put some cement grout in that hole. And after that, what we can do is that we can put some cap over it. We put some soil nail cap. You can see this is the end product. Okay, slope. Here later I think they have shown. Okay, now let us see this one. This is very interesting. So first you see what? So this is a soil slope, right? You can try this at your home also. Okay, so this is a very easy experiment that we all can do, right? So it's very easy experiment. So at our home also, just we need some weight, some load, so I say this container and some soil, and to reinforce we need some long toothpick kind of thing. Okay, so just see. So what we are doing, so there is a slope here, soil slope, and what we are doing is that we are putting this load over it. Okay, putting some load over it. So we keep on increasing the load. So what will happen at point will come, we will see this soil actually starts on deforming, or the slopes continues to fail. Okay, so they are putting the load, putting the load, putting the load. Okay, so they increasing the load, you keep on increasing the load. So see, now see, it has started to fail. Okay, so at when the load reaches, in their case, when the load reaches around 26 kilograms, what happens? It starts to fail. So again they've increased. Now see continuous deformation of the, so see, it just fails, right? The soil slope cannot take the this load anymore. Now what we will do is that we will reinforce this slope. Okay, see, you can do easily, you can do this at home, but you just use some long stick, thin stick, long toothpick kind of thing, whatever. Okay, very thin sticks you can use to reinforce the soil. Okay, just put it like this, we put it like this, and what we are doing is that we are reinforcing the soil. Okay, so like this you can put the sticks, and now again we keep on loading. So we'll see that if we put huge amount of load, then also this soil won't fail. What happens in their case, whatever due to disbalance, this weight actually falls out, but the soil does not fail. Okay, this load will actually this fall out, but this soil won't fail. Let's see. Okay, so 26 kg is achieved. Okay, but still now this soil hasn't failed. The soil slope has not failed. We increase the load more, increasing the load more, but still now you can see the soil slope has not moved by 1 centimeter also. Okay, it has not even moved 1 centimeter even. It's so firmly it is holding up. Okay, see their weights have fallen, but this soil slope is undisturbed. Okay, due to this balance, these weights actually fall down, but with this huge this stack, right? But this there is no movement of this soil slope, not even little bit movement of the soil slope. So now I think you can visualize how this soil nails or reinforcement actually helps to hold the soil in place. Okay, to reinforces the soil. Okay, so this is a very interesting and easy experiment that we can always do at our home. All right. Okay, so next, this what is the concept of reinforced soil? Okay, we had already studied in the previous week the concept of reinforced retaining walls, right? We already studied that. So here you can see if the number of layers of reinforcement are high, then what happens? The soil becomes stiffer and stronger, isn't it? The soil is becoming stiffer, it is becoming stiffer and stronger. We increase the reinforcement, it's becoming stiffer and stronger. Okay, so heat is the unreinforced, this is the reinforced with 5, right? So higher strength for reinforced, more number of reinforced, more strength for the soil. Now, if I ask you what are the two concepts, okay, what are the two concepts using which we actually explained this increase in strength of reinforced soil. What were those two concepts? If you can remember, we solved last week. Last week we had solved some problems, and we had also we had also uh, discussed in detail, right? So, what were the two concepts? What were the two concepts using which we can actually explain this increase in strength of reinforced soils? What were those two concepts? If you remember, can you say what were the two concepts?
Rupture and pull-up.
Yeah, rupture and pull out.
Yeah.
So those two were explained by two concepts, right? So rupture was explained by one concept and pull out was explained. So one concept was increase in friction angle concept, another was increase in apparent development of apparent cohesion. So those were the two concepts. Okay, then here we see some types of who was the this who was the first person who actually developed the concept of reinforced soil wall or earth wall? Who was the person who developed the concept of reinforced earth wall?
Mr. Vidal?
Yeah, it was Henry Vidal. So he actually patented this term reinforced earth wall. So hence generally we use the term reinforced soil wall so that there is no contradiction. Right? So next, you can see here some types of wall facings, right? So here we have full height panel, we have segmented panel wall, we have modular blocks and geotextile wraparound. So this first is the full height panel wall means what? Means this whole panel is actually constructed, casted at some place and then taken to the site as a whole unit. So it is very heavy and uh, very heavy also, and this transportation is also quite difficult in that case, right? And the main disadvantage is that it is a whole, it is a one unit, right? So it doesn't allow any movement, so it is very stiff structure. So what so this so whereas this segmented panel wall will see, these are made up of certain smaller segments. So these smaller segmented walls, these are easier to construct because easier to place, and there it allows some movement of this between these panels, so that due to that actually this there are less chances of failure. And then again, the third thing we see is the modular block wall. We already discussed it. Modular block walls. These are some small brick-like blocks, heavy blocks, obviously large, much larger than bricks. So we just keep on placing them one over another, and we place the geosynthetic layer between the soil and between these layers, and in that way we construct this wall. And the third is the geotextile wrapped retaining wall. This is nothing but we just wrap around this retaining wall and keep on wrapping it. Okay, put the soil, wrap it, put the soil, wrap it. But the main disadvantage of this is that as what happens if some uh, miscreants come and just cut this damage this geotextile or geosynthetic, whatever it is, geosynthetic they have used. So they can easily damage it from outside, right? They can cut it, they can burn it, whatever they can. They can pull this out. It's will try to pull it out. So many things can happen. So in that way, it will be a huge. It will be risky, right? So the reinforced soil wall may fail if you damage the reinforcement. So in that case, what we do, if actually don't leave the wall like that, we put some this put some facing blocks at the front. Okay. So as we discussed, this reinforced earth wall was actually earth concept was actually given by Henry Vidal in 1963, and after that, gradually all around the world, in abroad as well as in India, this concept started growing. So 1960 means around I mean, not that much here. Okay, so in just in 2006, the first geogrid was actually manufactured in India. So you can see that in India, this manufacturing of geosynthetic is not that old concept, just 15, 16 years, 16, 17 years old. Okay. Okay. Then next we have the types of reinforcement. So what are the types of reinforcement that we can use? One is geosynthetic, another is steel. Okay, steel reinforcement and geosynthetic reinforcement. Okay, and in geosynthetic reinforcement, what are the different types of geosynthetic reinforcement that we can use? Can you say name some? What is the main major type of geosynthetic reinforcement that we use? What is the major type of geosynthetic reinforcement?
Polyethylene, that
Huh?
polyethylene,
No, not the material. I'm just asking the types, main broad area of geosynthetic.
Geotextile.
Yeah. So main is this geotextile. Another one is the geogrid. So these two are
Geogrid.
geogrid. This geotextile and geogrid. These two are the widely used. And other than that, you can use some polymeric just strip. So this polymer, the strip of this polymer material, the strips you can use. Okay, and then we have the steel reinforcement. Okay, then steel reinforcement also you can use steel strips. Okay, so steel strips you can use, and steel meshes you can use. Okay, steel mesh you can use. But the main issue with the steel is, what is that these are like very prone to damage. Okay, so you should select the steel in such a the grade of steel in such a way that it can withstand this weathering effect. Okay, if water goes inside, it will get corroded easily, and due to this corrosion, what will happen is it will become weakened, right? So all those things we have to consider while design. Now for this for low height for heights for walls with lower height, is geosynthetic geosynthetic reinforcement is actually cheaper. Okay, and if the height is actually quite high of the retaining wall, then both actually give almost the same cost. Okay, okay. Now one more thing is the other differences. Okay, the main differences between the reinforced soil wall and the conventional. So flexibility, obviously you can say that reinforced concrete walls. The RCC walls are less flexible, and this reinforced soil walls will be more flexible, right? Then settlement, see this reinforced reinforced soil walls can have some slack, have some this what to say, scope of settlement, right? But this what will happen as these RCC walls are not flexible, they won't allow much settlements. Okay, this maximum height, so you can reach only up to say 10 meter with RCC retaining walls, but with reinforced soil walls, you can reach almost up to 100 meters height. Okay, so construction reinforced soil walls, it's easier construction. Okay, even unskilled labor you can use for that. Pace of construction is also very faster in case of reinforced soil walls. So it depends on mainly on the backfill soil that you can bring. Okay, the speed of at which you can bring the backfill soil and compact it, that is directly proportional to the speed of construction. Okay, and place of construction, you can all construct it almost at any place. Okay, foundation is not required. You don't have to construct this foundation separately above which you need to construct a wall. Just you need a general leveling pad, say of PCC concrete. You construct a leveling pad, and above that you can just construct the this reinforced solutions. And this seismic response, see, these reinforced concrete structures are very heavy, right? So these are also prone to failure due to seismic activity. But as they as these reinforced soil walls are highly flexible, so they can actually undergo large deformation before failure. Okay. Now next we come to the different wall configurations. Okay. So some basic configuration you all know. See, say this is the wall. So normal full height configuration. Okay, this is the general configuration that we use, the most basic configuration. So this is the soil and these are the reinforcement. Okay, then we have the stepped wall configuration. So here we have some length here. Then we have this trapezoidal wall configuration where top we have higher reinforcement. So, smaller. Okay, then this part height means what? Say you have some uh, soil here above this portion. So just this below this part, you just reinforce the soil, and this portion can stand on its own. You're not reinforcing this soil, but you're reinforcing just this part of the soil. Okay, then this back to back. See, these back to back retaining walls are used widely in this road approaches. Okay, the highway approaches that are constructed, they are what we do. These approaches we need to construct, right? In that approaches, these back to back walls are constructed. So this reinforcement comes from this both of these. So this side also, and the approaches like this. Say the approaches like this. So we are constructing wall here also, here also. So in the middle, we have the reinforcement. Then apart from then we have tired walls, bridge up for, and also for these walls for bridge up. Okay. Now, what are the basic components of the reinforced soil walls? Okay. What are the basic components? So say this is the facing blocks, right? Then you have the soil. This soil is divided into two parts. This is the reinforced soil and this is the normal backfill soil. Okay. This is the reinforcement that you are using. So this is the reinforcement. These are the reinforcement. And below we have the foundation soil. So foundation soil, backfill soil, reinforced soil, reinforcement, and the facing blocks. Okay, and also this leveling pad. So these are the main basic components of the solid walls. Okay, reinforce a little. Okay. Just let us. So this is a construction video. Okay. So in this video, it's shown how the complete process starting from casting of the facing blocks to the construction of the this complete reinforced soil retaining wall. So this is shown here. So let us just see this. Okay. Let us see this, and I will explain to you step by step. Okay. So this company Strata is like a very popular company. So they manufacture this geosynthetic materials. Also, then also they help in designing these systems. Okay, it's a very popular company. They have done many projects in India. Okay, so here you can see approach road, right? So here at the top, you have the pavement which carries the vehicular load. Okay, so this is the approach road at the top, and this is the side. From the side, you are seeing the this approach road. So this is a common sight, right? Whenever we travel in the highways, we see this. We see this. This is what we see from the side. If you travel in this arterial loads on the side and not on this flyover, you can see that this kind of facing. So these are nothing but the facing blocks. Okay. So they are nothing but the facing blocks, and these facing blocks are not ordinary concrete blocks. These are RCC. Okay. So these are made up of RCC blocks. So at the base, what we do, we put some leveling pad and we start putting this uh, with the help of crane, what we do, we place uh, these facing blocks. Okay. And facing block, behind the placing blocks, we have hooks, and with the help of the hooks, what we do, we tie the reinforcement. Okay, we tie the reinforcement with the help of the hooks. Okay, this is what they are showing. This is showing this what they're showing here is that this construction of this facing block. Okay, the construction of the facing block. They are showing. This is the reinforcement of the facing block. Okay, so nominal reinforcement is provided, right? And here they are spacing some spacers. Obviously, we need to put some spacers, right? So same way this slabs and a normal construction. Okay, the spacers they are placed, and this is the mold. Okay, so there is some mold. So first we clean the mold. We clean the mold. This is the mold. The mold using which these facing blocks are constructed. All right, this is the mold. So we place the reinforcement into the mold. You can see the reinforcement is at the center. Okay, with the help of these spacers, what we do, we have given some gap at the top and bottom. We need to give some clear cover, right? So with the spacers, we maintain the clear cover, and we have put the reinforcement inside this mold. And then what we do, we just cast it. Okay, you put the concrete. You then vibrate it with the help of some this needle vibrators or something, and we compact the concrete. What happens? These facing blocks are formed. Okay, then these are the hooks. Okay, these are the hooks or the connectors that are constructed while casting the facing blocks. So these connectors are also very important because we need to tie the reinforcement somewhere, right? So okay, I will just, and this we just finished it. I will just come to it. Okay, so we just here we are just providing these connectors. All right. So you can see that this is the completed construction for of these facing blocks. Okay, the construction of the facing blocks are complete. Then we allow for it to queue out. Now, Okay. Now see, now we need to start constructing this wall. So before we start constructing this wall, the first thing we need to do is that we need to make this leveling pad. Okay. Okay. So see here, this part is the excavation. So this is the main ground level. So little bit you have excavated down. A little bit you have excavated down, and from the excavation you need to there need to be minimum of half meter distance, and after this half meter distance, what we can do, this part, in this part you can construct the PCC. This is the plain concrete leveling pad. You can start constructing. Okay, see, just this is the formation of the leveling pad. Just normal PCC construction, not RCC, normal plain concrete construction. What we do, we just to get a level surface so that it's easier to place the blocks. What we do, we construct this leveling pad. So this will be as per the drawing only, as per your requirement. And now see, these panels are actually constructed to this casted somewhere else, and then they are brought to the site using these trucks. And with the help of the cranes, we move these panels. Now see, now here like that. So this leveling pad actually gives a plain area for us to place they place this wall facing panel, right? So what we do, we place the panel. Okay, like that we place the panel first. Okay, so generally little bit batter is given towards the soil, because uh, after the soil is filled and everything, right? So what happens, it actually eventually becomes straight. So initially a little bit batter is actually given towards the inside, towards the inner sides. Okay. Okay, and these wooden clamps like these wooden clamps are actually used to hold the panels in upright position. So these are actually fixed like that, and you can see here in the images that were shown by Professor Rajagopal during the classes. Also, you would have seen this kind of wooden this type of clamps, right? So these clamps are actually used to hold this uh, these panels in position. Okay, now what we do is that we put some this non-woven kind of geotextile with glue. Okay, we fix this non-woven kind of geotextile in the joints. Okay, we glue them. So this is done because so that the soil actually does not come out of the gaps between the two. So when you place these panels, what happens, there is slight gap between them. So to prevent the soil actually coming out of that gap, okay, soil coming out of that gap, what we do, put some geotextile in this gaps. We glue we fix the geotextile with some glue. Okay, so after the soil is put over it, so obviously this is going to stay in place, right? So even if the glue wears out, this will stay in its place. So what we do, we put some geotextile, glue some geotextile in this joint so that the soil actually does not go out of this joint. So if you do not put that, what will happen is that little by little the soil will keep on coming out of these gaps, and it will slowly, as time passes, a large amount of soil will come out and it will just form a slush outside the. Okay, so it's very bad to look. That's why, and also for this prevention of erosion prevention, this is good. Okay. Well, then what we do, then we this water this area, and we compact the soil, compact the original base of the base soil. We compact it with the help of the roller, and just you pay attention here that this roller is actually not going very near to this facing panel. This is very important. Okay, this is very important. If the roller goes very near to this facing panel, what will happen? There are high chances that this spacing panel will actually fall out or something like that will happen. Okay, there are high chances of damage. So what is done is that a safe distance is actually being has to be marked till which the roller can actually move. And in the remaining distance, these hand vibrators or hand compactors actually are used. Smaller hand compactors are used. Okay. See, the smaller compactors are used to compact the soil that is near to these spacing walls. Okay. So never ever this roller should be used. Roller should be used near to the spacing walls. Okay. Okay, and main one more thing is that if you see, if you notice here, these rollers are actually moving in this longitudinal direction, right? Are moving in this longitudinal direction and not in this direction. This is also one more important thing that we need to follow. This roller is actually moving. This roller is actually moving in longitudinal direction and not in the this lateral direction, in this direction. It is moving in this longitudinal direction. What will happen if we move in this lateral direction? The compactive force will be so high that these panels will actually fall out. Okay, with the pressure of this compaction, what will happen? This will fall out. So it's very essential that this roller is actually moved in the longitudinal direction and not in this other transverse direction. Okay. Okay. So here, see initially, see there are see here they have shown one type of this clamp. Okay, here they have shown one type of clamp. These type of clamps are what? These type of clamps are hollow from inside. Okay, hollow from inside. So what we can do, you can put the strips from one side and you can take out the strip from other side. This is one type of clamp. Okay, this is one. See, these were originally casted. Okay, when we use, if we had also used this as spacer, right? So when we are casting it, what we have put this inside. We had put this inside while casting only. Okay, we have put these hollow clamps inside while casting only. So we put from one end, if we put the GSM3, it will come out from the other side. This is one type of clamp. And another type of clamp that is used is that outside only, like the type of clamp you use to hang your fan, right? That type of clamp can also be. Those are rod side, like bend rods, small this clamps that are fixed outside. Okay, that is one more type of clamps that can be used. Okay, like this, one more type of clamp can also be used. So if you use that kind of hook kind of clamps, what you can do is that you can just you can put the geosthetic material and pass a rod over it, and that rod, see, clamps are like this, right? And you can imagine, say, how to show. So this is the gap between the geogrid. So the geogrid goes inside, and in that hole, here what we do, here you put one rod. Okay, here you put one rod, and that rod actually holds the geosynthetic material in position. Okay, but here you see, here whatever they're using is they're using this polymeric strips, kind of polymeric strips. So you put put from one side, you roll out and bring it to other side, and fix in the other direction with the help of these pegs. Okay, these wooden pegs. Then we put one more layer, then we compact it again. Then again one more layer. Like this, we keep on continuing. Okay, and these are some pads. These are some elastomeric pads that are actually used between these facing blocks. Okay, to just to place these facing blocks, these are used at the interface of the facing blocks. Okay, place these elastomeric pads, and above that put the facing. Okay, same process. We clamp it, put wooden clamps first just to hold that in position, and then we paste this geotextile here. Same process is just repeated again. Okay. This is one more thing. What they have done is that they have placed a geocomposite. Okay, the geocomposite layer behind the facing panel. So you can see here. So this is the cross section. See, this is the geocomposite they have placed. You can see here. Okay, this is a geocomposite. So can you tell me what is the purpose of the geocomposite that is been placed here, placed behind the pad? There are two purposes of this geocomposite. Can you tell me what are those purpose? What is the purpose? Yeah, what? Yeah, one is drainage, and what is the other? Yeah, correct, correct. Yes, correct. One is drainage, another one is filtration. Okay, if you see that geocomposite, it is nothing but inside they have put one geonet, and on the front and back they have put some geotextile. So the geotextile will act as a filter material that won't allow the soil to pass through it and only the water to pass through it, and the geonet will aid in drainage of the water. Okay. Same construction. Okay, so this is the final view. Done. Then top, what we do? This At the top we put one coping beam because we need to put the crash barrier also, right? This coping beam is placed and the other things are casted. The crash barrier and the pavement. This okay. So this is how a complete reinforced arch wall is constructed. Okay. Now I hope that is clear, right? So very interesting also to see. What is the question? Is there any specific reason for providing Gabion facing for? No, okay, let me just open the image for Gabion. See, yeah, this seems to be so the yeah. So the main basic, see, there is no such basic part. The main reason these gabions are provided because that is natural, right? This these rocks are naturally available in a place where these rocks are naturally available. These gabion facings are much more economical. Okay, that is aesthetic purposes. One is aesthetic purposes. The second more important purpose is that it stops erosion. How it stops erosion? See, it allows drainage water to pass through it. Okay, naturally, what will happen? Water will be able to pass through it, but the soil which is being retained, that won't be able to pass through it. Okay, the water is able to pass through it, but the soil will be retained behind. So it will act as a filter and a drainage material. Okay, so first is because it is naturally available, right? It's naturally available in the even if it's available in the site, then well and good. So it's naturally available substance. Also, it gives a good aesthetic view. Naturally, it gives a good aesthetic view. Thirdly, it has good drainage and filtration property, and that is why these gabions are used. Okay, the only demerit is that maybe if we have to bring this gate thing from large distance, we means large these are heavy material, right? So you need to bring, and you might be able to. There might be need to break this or crush it to. If the stone is very large, then you have to crush it to smaller size and shape. So that is all. So generally, these are used for the Gabion walls are used for that reason. Okay, aesthetic purposes, naturally available, good drainage, so stops erosion of the soil. Yes, that is why these gabions are actually used. Okay, yeah, leveling bed material, yes. Leveling bed material is PCC. Okay, just normal PCC, just to get a level of the main base soil, yeah, just to get a plain surface, so that this level, so that this facing walls can be placed, right? Just to get a plain surface, what we do, we just put this, construct this leveling bed, nothing else. So, okay. Hmm, okay, so next we have, just, yeah. So next we have the codes and design standards for reinforced soil treatment. Okay, so the main code is our BS 8006, which is the strength reinforced soils and other fields British Code of Practice. So I think that is being updated now. I forgot the year, but I think after 2006 it has been updated once more. Okay, please check. And all of these codes, please check once. Okay, and on internet, just check the latest version only. Okay, so this all of these codes might have been updated. Just check once. So the first code is the British Standard Code that deals with the these reinforced soil structures. Then we have our this FHW, this Federal Highway Administration, this code that deals with the mechanically stabilized earth and reinforced soil slopes. Then we have one more, this segmented retaining walls national by National Concrete Machinery Association, and the seismic analysis on by NCHRP. Okay, these are all basic codes mainly given by Western countries such as USA and UK, that are widely used all around the world to construct the reinforced soil walls. Okay. Okay. Now, the this main two codes that are used, that are the BS 8006 and this Federal Highway Administration FHWA NHI 00004. Okay, these two are the main basic codes that are used for this construction. All right. So let us see the differences. So first is the BS 8006, and the other one is our NHI 0. So this BS 8006 is based on our limit state method. Okay, the main limit state method, and this FHWA is based on the lumped factor method or approach. Okay, okay. The BS 8006 actually covers everything, starting from this. reinforcement, polymeric reinforcement, such as this geotextile, geogrids, then the steel reinforcement, then reinforced walls, reinforced slopes, then anchored art, everything. This BS 8006 actually takes care. But this NHI actually does not comment on the anchored, okay, the anchored reinforcement. Okay, so BH 8006 is more vast in that point of view. But this main difference is that the BS 8006 does not consider this seismic effect, but this considers the seismic effect. Okay. Now, how are the these forces or stress forces or the loads are that are dealt that are actually different in both the cases? So as we said, PS 8006 deals with the limit state method, and this NHI actually deals with the lumped factor approach. Okay, lumped factor. This BS 8006 doesn't check for the overturning and eccentricity. So generally, if you remember from your soil mechanics or this soil mechanics class, or this design where we might have solved some problems regarding this design of retaining walls, or in the design for retaining walls. In that case, you might remember that you had done some checks for overturning and eccentricity, right? So that to comment whether the retaining wall is safe or not, you need to do this overturning and factor of safety, overturning and eccentricity check. Okay, those checks we had done. Generally, we do those checks. Versus BS 8006 actually does not check this, but the NHI 0043 actually considers those things. Okay, the overturning and the eccentricity checks. Now, as per this BS code, this vertical stress is nothing but gamma into Z plus WS. So gamma into Z, gamma is the unit weight, and Z is the depth. So unit weight into depth plus WS is nothing but the surcharge. Okay, it is the gamma Z. But this FHWA, this considers this vertical. Sorry, right? So this vertical load is RB by L minus C. So this RB is nothing but the total vertical load that is coming, and this length here we generally what we consider is that there we consider the length of the reinforcement that we are placing. Okay, so we will see all this in detail while we design the reinforced retaining wall. All right. Okay, so apart from that, both of these codes suggest different criteria. Yeah. IRC 102 also. So these were the initial codes that were actually given, right, by Western countries, and after that, Indian codes were actually developed. Okay. In which year was IRCSP 102 was given? I don't think it's that old. What is the, do you know what is the latest version of IRCSP 102?
It is 2015, sir.
2015, right? Okay.
Yeah.
So I think PS 806 and IRC, this one SP 102 are quite similar. I am not sure. Just please check once, compare once. This PS 8006 and IRC SP 102 should be quite similar, if I remember. I'm not sure about that. Please check once. Okay, the criteria for this BS 8006 and this RC1. Mostly these Indian codes are mostly taken from this British codes only. Whatever Indian codes we are studying, na, this RC, is IS 456 and all those things, whatever codes that are, most of these codes are generally taken from British codes. Okay, so mainly initially they were initially adapted from British codes only. So I think that BS 8006 and this IRCSP 102 are should be quite similar. I'm not sure, so please check that once. Okay, so yeah, so then also one more thing we need to consider is that this soil gradation requirements. So, soil gradation requirements for both these codes are actually quite almost they're quite similar. Okay, and all of them suggest the optimum amount of this number, optimum size of quantity and size of soil particles that should be there in the backfill soil. So while construction of reinforced articles that should be considered. Okay. Then we have the electrochemical properties. The electrochemical properties. So as you all know, why are electrochemical properties important? Electrochemical properties of the reinforcement of the soil is important because as when you are using this reinforcement of the soil, the chemicals present in the soil tend to react with the reinforcement. Okay. So due to that, what might happen is that the reinforcement might get weathered or damaged. So due to that damage, the say you do some design, okay, design and you have constructed the soil, you are constructed the wall, and you are like, okay, my design is completely perfect, my wall won't fit. But you did not consider that the soil was highly acidic in nature or something like that. What will happen? The soil will actually, soil is going to damage the reinforcement. And if the reinforcement gets damaged, okay, if the reinforcement starts getting damaged, it's going to the soil wall is going to get collapsed. So it is very important for us to consider the electrochemical properties of the soil. Okay, the backfill soil also. So there are many. So the uh, so for us to use steel reinforcement, the electrochemical properties that we have to consider are more stringent. Okay, because steel, see, these polymers are less reactive. Okay, generally less reactive, and but this steel, as it is metal, it is more reactive. Okay, for that purpose, this criteria for electrochemical properties are more stringent when we use this steel reinforcement. Okay, and so you need to have follow this certain resistivity criteria, pH criteria, chloride content, sulfate content, organic content, and plasticity of soil. Okay, so all these things are important when we consider steel reinforcement. And when we use some polymeric reinforcement means any kind of geosynthetic, say geogrid or geotextile, whatever you use. In that case, we need to see that the pH, you need to consider that the soil pH is within the range, and also the plasticity index of the soil is within the range. That's all. Okay, so the criteria is more stringent when you're using the steel reinforcement. Okay. Now, what properties should the backfill soil should? Okay, so these properties, some properties actually we can say quite intuitively, right? So what properties? So what do you think? Uh, what kind of soil shall we use? We should use granular soil, or we should use little soil with fine grain. What soil should we use? Granular soil or fine grain soil for backfill as a backfill? Granular soil or fine grain soil? Which soil should be more appropriate? Which type of soil would be more appropriate for backfill to be used as a backfill soil? Granular. Why granular soil? Why granular soil? friction angle. How friction angle is this one? See, one friction angle. So there might be two explanation for friction angle. The one friction angle is the friction of the soil. Okay, the soil strength. So inherent strength of the soil is high. Okay, okay. So inherently, if higher friction angle, granular soil have higher friction angle. So the inherent the inherent strength of the soil is high. Okay, fine. And in what other way this friction angle actually influences the property, influences the behavior of the reinforced soil structure? One is the inherent strength of the, if high granular soils, that means high friction angle, that means inherent strength of the soil is high. Okay, what is the other way it's affecting? Yes, yes. I also think. Okay, I'm not, I also think that only I said the RC this SP102 actually follows BS 8006. Okay, I also think that. I am not sure. Just check it once. Okay, I'm not sure. Just check it once. So granular soil, higher phi, higher inherent strength of soil. One more thing, higher phi, so higher delta means higher frictional strength mobilization between the uh, reinforcement and the soil. Okay, so higher this frictional stress shear strength mobilization between the reinforcement and the soil. Okay, that is what. Now come to the this is for phi, right? Now let us come to the second. If you are using granular soil, then higher permeability, higher permeability. So what? Higher drainage, inherent drainage property. So it will allow the water to pass through it easily, right? Higher permeability. Then lower plasticity index. Lower plasticity index means what? Lower volume change. Okay, it is not, the soil won't expand and contract that much when it comes with contact with water. Lower plasticity index, so lower volume change means the reinforcement is going to have a higher service life. Okay, but this is not, there should not be the case that what you do, you bring highly angular blocks of large blocks of aggregates and you put that as backfill soil. You cannot do that. Okay, that's why there is also upper limit for that, because you cannot, why you cannot do that? If you put heavy big blocks of stone or rocks, a highly angular, maybe say highly angular, what will happen? That is just going to damage the reinforcement. Okay, that is going to damage the reinforcement. So for us to use the backfill soil, we have to avoid that. Okay, so there will be high installation damage, and in the long run also it's going to damage the reinforcement very fast. So you should not use soil with very large particles or highly angular particles. Okay, large particles. Okay. Now the most important question. Okay, this you should be able to answer, because this is highly conceptual. Now, which friction angle of the soil should be considered, and why? What did you send? Okay, okay, okay. Thank you, Mr. Mohammed. Okay. So which friction angle of the soil should be considered and why? So generally what we do, generally the soils are granular, right? Yeah, generally the soils are granular. So what we can do, you can use direct shear strength values. Okay, we can do direct shear strength test, direct shear test. We can get the values of phi. Now, which phi to actually use and why? Say we have shear stress, shear stress. Okay, this will be something like that. Okay, why peak value? Why should we use peak value? Why should we use peak value? And why and when? The question is why and when should we use peak value? When should we use peak value and when should we use this residual value for the constant value volume? Why and when? You are first you said peak value. Okay. When should we use peak value and why? First is when should we use peak? If you just turn on your mic and speak, there is no problem. Anyone can turn on their mic and speak anytime. When should we use the peak value and why? This is for direct shear test and say for uh, why should we use peak value and when? So see, generally if the soil is strong, generally if the soil is strong enough, so what will happen is that, okay, if the soil is we are using the this for steep slopes at this retaining wall. So you are using where you need to use the phi value where you are constructing a retaining wall. So in that case, what happens? This strain or the strain that occurs in the soil or the displacement that occurs in the soil is quite less. So it is lesser. So that's why what we are using this peak value. Okay, and for this shallow slopes and for soft soils or for structures on soft soils, what will happen? Large amount of strain is actually okay. There is large amount of strain that actually takes place. Okay, shallow slopes, the soil is weak. Shallow slopes or for where large this or for structures that are constructed on soft soil. For that case, there is a tendency for large amount of strain to get mobilized. So hence, what we do, you use this residual. All right. So for steep slopes, that is inherently the soil is strong enough. So for steep slopes and for where you're using retaining walls, the tendency for displacement is less. The strain development is lesser. So you tend to use peak value. And for cases where this the slope is shallow, okay, the inherent slope is shallow where you're constructing something over soft soil. Okay, in that case, there is high tendency of displacement. Okay, high strain is developed. In that case, what we do, we choose this residual value. Okay, okay. Now next, we have this earth pressure. Okay, so generally the earth pressures which affect this reinforced soils, retaining walls or something, those are Those are our active earth pressure and our earth pressure at rest. Okay, these are the two things that affect. Okay, so this active earth pressure actually develop to mobilize the active earth pressure. Very small strain is required, as you all should know from the basics phenomenon. Is very small strain is required to mobilize this active earth pressure. Okay. Okay. Now, sometimes what I mean, sometimes uh, just a, just a second. No? Yeah, yeah. So uh, generally, what that affects our construction is the active earth pressure. Okay, active or the earth pressure at rest. So generally, in most of the cases, what you take into consideration is the active earth pressure. Okay, and in some cases where this there is incremental construction, what happens is that the top may not deform as much as the center or the bottom of the retaining wall. In that case, what we do is that we use the active earth pressure at rest. Some portion we will use the active earth pressure at rest, and the other portion we will use the this active earth pressure. Okay, so where the deformation is not that much, where the deformation of the soil is not happening that much, there we tend to use the earth pressure at rest, and where there is some amount of deformation that is taking place, we use this active earth pressure. Okay, now active earth pressure. So you know what is the active earth pressure coefficient? What is the this one for relation between the active earth pressure coefficient and phi? 1 minus sine phi by
1+9.
1 plus sine. Right? Now, for a C phi soil, what is the earth pressure that is acting? Sigma x, it is nothing but K into gamma into Z minus YC root over K plus K into Q. So this is nothing but gamma into Z is the overburden pressure, effective stress into K minus 2ic root over K, that is due to the cohesion that develops, plus K into Q. Generally, in the backfill, whatever backfill soil we consider, we do not consider the C value. Okay, we consider granular soil, it doesn't have any cohesion, and also we don't consider this C value in our design generally. Okay, so because of that, our this lateral earth pressure is contributed mostly by this quantity and this quantity. So this quantity actually comes from the surcharge, and this is due to the overburden of the soil. Okay. Now there, as you know, there are many earth pressure theory. So Rankine earth pressure theory. Okay. Then Coulomb. Then yeah, Rankine and Coulomb. Okay, these are the main earth pressure theories that were given, right? So from Rankine's theory, so I won't just write down these equations. Okay, this will be just models. We just go through this. So Rankine had given some equation for Ka. Say if you have a inclined backfill soil, you have some this inclination for some expression for Ka. Right now, Coulomb had given what Coulomb did was Coulomb actually considered the friction. He considered that there is some friction between the soil and the retaining wall. So in that case, he gave some other expression for K. Okay, so Rankine considered that there is no friction between the wall is smooth. The wall is smooth. That is, there is no friction between the wall and the soil. And Coulomb actually considered that there is friction between the wall and the soil. Okay, so what is the say you have a retaining wall, okay, and you have a backfill and the backfill is inclined at angle beta. So what is the maximum value of beta that is possible? What is the maximum value of beta that is possible? You have a retaining wall, you have a backfill soil with incline. The backfill is not straight, okay, it's inclined at angle beta. So what is the maximum value of beta? Yeah, the maximum value of beta is 5. Why it is 5? Can beta be more than 5? Can beta be more than 5? No, right? Because the soil won't be, yes, it will collapse. So the maximum value of beta is nothing but 5. Okay, then we have the design load. So design loads you need to take consider the self weight, the live load. Okay, the live load due to the point loads or say uniformly surcharged. Then the horizontal load that might come from the crash barrier, that also you need to consider. Okay, so see here, see you have the soil, right? You have the retaining wall, you have the retaining wall, and here you have the crash barrier. So here you have the pavement. Okay, so there is some horizontal load that might come when a vehicle crashes into the crash barrier, right? So that load you need to consider. Then these vertical loads from bridge abutment, the seismic loads, all these things you need to consider. Okay. Now stability consideration. For stability calculation, what are the things that you need to consider? Lateral sliding stability, overturning stability, bearing capacity failure, and the overall failure. Okay. So sliding means what? This whole retaining wall is going to slide. Okay, the whole retaining wall is going to slide. So you need to ensure that this retaining wall does not slide. Okay, then we have the overturning. So you need to ensure that the retaining wall actually does not fails in overturn. Okay, there is no overturning failure. Then bearing capacity failure means what? You need to ensure that the soil below this below the retaining wall does not fail in bearing. Okay, the soil is strong enough so that it can hold the retaining wall and the backfill soil in the space. And then we have this slip circular overall failure. Okay, say we have a retaining wall here in a slope. So if the slope is weak, there might be overall slip failure like that. Okay, there might be a slip like that. So that also you need to consider. Now there are various load combinations that are given, the partial load factors that we need to consider. So all this we will see in detail while s- we deal with the designing of the retaining walls. Okay, so there are various combinations A, B, and C. So A combination consider some loads, B combination consider some loads, C combination consider some loads. So according to our requirement, we need to use that. Now let us solve some C. These there are no problems from this topic. Right? So let us just solve some problems for the retaining wall, normal retaining wall topic. Okay, earth pressure theories. Let us just try to solve some easy problems. Okay, so you should solve these problems by yourself only. You should first try to solve this problem because these are very easy soil mechanics level, normal basic soil mechanics from the basic soil mechanics course. So you should be able to solve this by yourself. Okay, so please try to solve the first problem. So retaining wall 6 meter high retains a cohesionless soil with the angle of internal friction 35 degree. G is given, N is given, N is nothing but the porosity. The surface is level with the top of the wall and the water table is 2.5 meters from the top of the wall. Just determine the active earth pressure per meter length of the wall. Okay, just try to solve. First, N is given, right? N is given as 0.405. So from that, what you do, you determine E, the void ratio. First of all, determine the void ratio. Let's try to recall the relation between E and N, the void ratio and porosity. What was the relation? E is equal to N by 1 minus. So now you can calculate void ratio. Please tell me what is the void ratio? This is the void ratio. What will be the
Point
void
eight
ratio?
one eight.
How much?
0.818.
Oh, 0.405 divided by 1 minus 0.405. 0.68, right? 0.681. It will be 0.681. Okay, then you consider find out the dry unit weight G gamma W by 1 plus E. Please find that out. G is 2.69, gamma W you know 9.81, 1 plus E. You can find out dry unit weight. After you find out dry unit weight, uh, find out the this submerged unit weight. Find out submerged unit weight. Then after you find out submerged, find out K. Please keep your calculators with you. Okay. So first you tell me what will be K. K is 1 minus sine pi by what will be K? 0.271. Gamma D will be so you have a 6-meter high rotating wall up to 2.5 meter. It's dry, and below that you have water. Okay. We need to determine the active earth pressure per meter. So for the top portion, what shall we have? shall have some triangular variation. What will be this? 2.5 into gamma. What is gamma? Gamma D. 15.7 into Ka. Right. Below that, this one will be same 2.5 into 15.7 into K. Then we have 6 meters, right? So 6 minus 2.5 is 3.5. This one is 3.5 into some. What is the submerged unit weight? 0.86. Okay. And rest is due to the water, right? So 3.5 sorry, 0.5. Yeah, correct only. 3.5 into 9. See nothing but gamma. So we have 1, 2, 3, 4. Okay. Now if we take all these areas, if we calculate all the areas, what we will get? We will get the total electric thrust. So let us calculate that. P1 is equal to area of that triangle, first triangle, so half into 2.5 into 15.7 into 0.271. Give me 5.271 into, wait just a second, 0.271 to gamma D. What is gamma D? 7 to 5. 2.5 half into K gamma D 0.5 square. So half into 0.27. So gamma D is how much? 30. Similarly, P2 2.5 into 15.7 0.1. Sorry, 3.5 because this height is 37. Similarly, you will get P3 area of this triangle 16.37 P4. Just you can see that this this is due to this P4 is due to water, right? Just you can see if you compare all the values, just see how much is the pressure due to water. It's huge compared to all, right? So water is like water is the number one. Water is our number one enemy. So always whenever we construct a retaining wall or any retaining structure, what we need to give special attention to the drainage of water, because this water, this water thrust due to water is huge. Okay, so you always need to give proper attention to the drainage of water, so that water does not get accumulated and there is proper drainage of water. So now if you all add all these P1, P2, P3 and total P active earth pressure will come out to be 126.99. Okay. Okay. Now, if it is asked to you, where is this P acting in this wall? Where is this P actually acting? Is acting at some distance y from the base, right? So where is this acting? So what we can do is that we can find out this y by just taking the moment, say 13.3 moment, just getting the centroid, right? We'll just do it for you. Zero mark. The total PA is equal to nothing but Q 1.68. So this PA is actually acting at 1.68 meters of the base. Okay. Now next, for the retaining wall shown in figure, find the active thrust and line of action. So here we have two types of soil, both are granular soil. You can see both the soil are granular soil, and for both the soils this C is 0. Okay, both the soil are granular soil, and for both of them C is 0. Okay, so for both of them C is 0. And we have different phi. For top soil phi is 30 degrees, and for the bottom soil phi is 35 degrees. So we will have two Ks, right? So what is Ka1? Please tell me what is Ka1? 1 minus sine 30 by 1 plus sine 30. We'll have 1.33, right? 1 by 3. 0.33. And what is Ka2? We just found out previously 0.27. All right. Now, see, this is submerged. See, water table is there. So means this is submerged. The below soil is submerged. So let us get the submerged unit weight for that. So 19 saturated is given. 9.81. Now let us try to draw the pressure diagrams. Okay. So top 3 meter will be having something like this. What will be this? 3 into gamma into 0.33. Right? 3 meters. Then bottom 3 meter. First you will have this rectangular arrangement, which will be 3 into 16. Now it will be K2. It will be 0.271. Right? Then again we will having some triangular arrangement, triangular force here. It will be nothing but 3 into 9.19 to 0.271. And last we have the water pressure is nothing but 3 to. Okay. So let us mark this 1, 2, 3, 4. Right. So we need to what we need to do is that again we need to determine where our is actually active. Okay, some distance y, so we need to determine where the PA is. Again, what we'll do similarly, we will find out P1 again. Area of the this first triangle, nothing but half K1 3 square into 60. That will be P2. It will be 3 into 16 into K2 to that will be P3. It will be half into 3 square into 9 point how much? 9 into 2. That will be P4. P4 will be half into 1W. Okay, now if we calculate all these one by one, we'll get the values 23. 6, 31, 11.21 and 44.15. Again, you can see this water is contributing to the maximum force to this active thrust, right? So water is contributing maximum. So total PA you can get by summing all this up. Point. Now to determine y, again we will what we will do, again same thing we will do. Summation PI YI by summation by write it as A, we get it as 1.6. Okay. So water is the maximum contributor. If there is water, we need to drain that out. Okay, here soil mass is retained by a smooth incline wall of like 6 meter high. The soil has a bulk unit weight of 20 kilonewton per meter cube and an internal angle of 60 degrees. The top of the soil is level with the top of the earth. If the soil carries a uniformly distributed load of 4.5 kilonewton per meter square, it comes the total active thrust of the wall per meter cube. Same, right? Same, exactly same as this other part. Okay, so what we can do is that see this. But soil is our retaining wall is like this. Right? This is 18 means this is 18. So this is we can get so this is AC we can get. Water is there or what? No, so no water is there. So what will be K? K is 1 minus sine 16 by 1 plus sine 16. It is 0.56. So first, due to the surcharge, 4.5, we have the surcharge. Due to that, this will be Q into K, right? 4.5 into K. Next, we have Q. Due to this, due to the soil, is nothing but this is 1, so this is 2, this is K to 20 into 6, right? We got that. Now let us find P1. Same area of this rectangle. So Q into K into height. What is P2? To half K is square into what is gamma? 20, 20, right? Gamma is 20. This one will be 15.33. This one will be 20. So P a dash is P1 plus P2. Now, this PA, see, this what we did was our wall is like this, right? So this PA with that PA dash that we determined, that is actually acting like this here, acting like this. But what will happen as it is inclined, our actual PA will be acting at some inclination like this. Okay, now this PA is nothing but the resultant of the weight of this soil wedge. So this is nothing but PA dash square, PA prime square plus weight square. Okay. So what is the weight? Weight of this wedge half into 6 meters into this AC distance. AC is nothing but 6, 10, 18 degrees into 20. 1 meter, say this in this direction 1 meter. So it will be 116.97. We have W, we have PA dash. PA you can get. What will be PA? PA will be 249 kilonewton per meter. Okay. So first we got PA dash acting at this line BC. Then what you can do from there, you can get the PA using the weight and the PA dash. All right. All right. Now, in order to get this angle alpha, the inclination of PA with the horizontal, what we can do, alpha is equal to tan inverse W by K dash. You can get alpha. Now also what one more thing that we can find out is this point of high point of application, this y distance. Okay, this y distance same as before. What you can determine 3 plus just by taking the moments and getting the centroid. Okay, so this PA and this PA dash is acting at a height of 2.07 meter from the base. So first what we did, we calculate PA dash, and from there we could calculate. Okay, done. Then okay, this will be the last problem. So this is basically for a C5 soil. So generally we do not use C5 soil as backfill for this reinforced soil walls. Okay, which you don't do C5 soil. Generally the soil is granular soil, just as 5 value. Alright. So here we will be just solving a problem for C5 soil. You can see a smooth vertical wall 4 meter retains a cohesive backfill soil with the bulk unit weight of this much and angle of internal friction 0 degree. So this is a cohesive soil. Okay, cohesive soil. Generally, we do not use cohesive soil for reinforced soil walls, but here just for the concept, just to recall the concept, we are just solving. Calculate the depth at which active earth pressure is 0, depth of tension crack, depth at which total active thrust is 0. All these things we need to. Okay, so I will just solve it. So we have a 4-meter wall, right? 4-meter wall, and see, for a cohesive soil, variation, the variation of this active thrust is really different, right? So it's a little bit like this. So at some depth Z naught below the top, the active thrust is actually 0. So that Z naught depth is given by 2IC by gamma root over Ka. So if you, so what is the Ka value? What is the Ka value? What is Ka value in this case? What is the active thrust coefficient of active earth pressure in this case? 50. 50. So K is 1. Okay, so Z naught will be twice C by gamma. So twice C by gamma, we can get this is 1 meter. Okay, 1.11 meter. Now, the first question is the depth. Calculate the depth at which earth pressure is 0. So we already found that out. The depth at the 1.111 meter below the earth pressure is 0. The active earth pressure is 0. Next is the depth of tension crack. Okay, the depth of tension crack is nothing but 2 into this H naught. So depth of tension crack is 2 into Z naught into 2 meters. Okay, so this is negative, this is positive. So this is into that what happens, some cracks develop. So that is the depth of tension crack. Now the depth, sorry, just a second. This Z naught, this is nothing but the depth of tension crack. Okay, because as this is negative, that is tensile stresses are coming, and as you know, a soil is weak in tension. What will happen, there will some cracks that develop in the soil. Okay, like some crack will develop in the soil due to tension. So the depth of tension crack will be same as Z naught. That is a depth at which this active water pressure is 0. The depth of tension crack is equal to Z naught is equal to 1.1. Now the depth at which total active thrust is 0 is nothing but this H. So if we take the total of this H, I total sum of the total summation of the total total force stresses in this region, what will happen? It will come to be zero. So here it's positive, where it's negative, so it's going to cancel out. So the depth at which active thrust is zero is h, which is nothing but twice into z naught. Okay. Okay. Now we need to find out total active thrust per unit of the wall when tension cracks do not develop. Just okay. So tension cracks do not develop means what? Do not develop means there will be some negative stresses acting here, there will be some positive stresses acting on the soil. So if tension cracks develop, what will happen? The soil is actually not in contact with the wall, right? So soil is not in contact with that wall. So what happened? The total active thrust total active thrust acting will be the area of this triangle. Okay, when tension cracks develop, remember that when tension cracks develop, what will happen? The soil is not in contact with the soil with the retaining wall in the upper portion. Due to that reason, the area of the total active thrust that is acting on the wall is nothing but a lower from the lower portion only, right? Because upper portion, the soil is not in contact with the retaining wall. So whatever active thrust is the soil is experiencing is from the below portion, is nothing but this area of this triangle. But now the question is when the tension cracks do not develop. Tension cracks do not develop means what? Means there is the there is contact between the soil and the retaining wall. Right, there is contact between the soil and the retaining wall. So due to that, what will happen? This and this portion is going to get cancelled out. This negative and this positive earth pressure, this negative and positive earth pressure that is acting on the retaining wall, that is going to cancel out. So whatever earth pressure is getting contributed is nothing but this area. Okay, if we just find the area of this trapezium, we will get the this get our this active pressure. Okay, in that case. So what will be this length? This length is nothing but k into gamma into h. H is not this one. Okay, let us say h naught h naught h naught minus 2ic root over k. So this is this length is nothing but 52. Okay, now what will be this length? What is this much? This is uh, this is nothing but 2 into 2 is I think 2 is it will be 20 kilonewton per. Okay, so how are we getting that? So let us go back and just go back a little bit. Where I do yeah, say say this is zero. Say this is zero. Z is zero. So what is kx? What is the earth pressure? Minus 2ic root over k. Right, only this portion is there. Minus 2ic root over k. Now if k is 1, what is that? That is at z equal to 0. If k is 1, q is 0. So for our case, q is 0, z equal to 0, k is 1. So earth pressure is minus 2ic, minus 2ic. So minus 2ic is nothing but 2 into 10, 20 kilotons. So this much is 20. So this much is also 20. 20. So now if we take the area of this trapezium, we will get the P. Okay. So the total electric is nothing but the area of this trapezium 52 plus 20 into, and this length is nothing but 4 minus 2.2 to 1.78 to 1.78. So we'll get PS 64.08. Okay, done. And similarly, to get the point of application of PA, what we can do, we can find out the this. You can use the formula for the centroid of trapezium and determine the y value 52 plus 2 220 by 3 0.5 meter from base. Okay, so this will be acting at this much meter from the base. So always remember that if tension cracks develop, that means what? The top portion, yeah, the soil is not in contact with the retaining wall at the top portion, so this whole area will come into picture on. Now, if tension cracks do not develop, that means what? This negative portion is also in contact with the soil, so this negative and this positive portion are going to cancel out, and only this trapezium is going to come to. Okay, so I hope that is clear to you. And with this, we will end today's session, and uh, so we'll continue whatever is being taught in this week in the next. All right. So with that, thank you for attending. And if you have any doubt, feel free to ask me anytime. And wish you a happy Independence Day. Okay. Thank you, Mr. Midin.